Hello everyone. Today we are discussing about the uh, syntax analysis phase in the compiler design. So the main role of the syntax analyzer is for the construction of a parse tree. So to know before the construction of a parse tree, we should discuss about the how the parse tree will be constructed and which type of the grammar will supports the construction of the parse tree. So in last class, I have explained about the different phases of the compiler design. That is, a compiler design consists of 6 different phases. First one is the lexical analysis, second one is syntax analyzer, third one semantic analyzer, fourth one intermediate code generation, fifth one code optimization, and sixth one code generator. So among these six phases, it has been divided into the front end and the back end. So first 4 phases, from lexical analysis to intermediate code generation, it will be considered as the front end, which is machine independent, and last 2 phases, that is the optimization of the code and the code generator, which comes under the back end, which is the machine dependent. So now we are going to be discussing about the second phase of the compiler design, that is the syntax analyzer. So the role of the syntax analyzer is to construct the parse tree which has been taken the input, which is produced by the previous phase, that is the lexical analyzer. So the lexical analyzer has been identified different tokens. These tokens will be given as the input towards the syntax analyzer phase. So here we can see the input towards the lexical analyzer is the source program. So by considering this input source program, the lexical analyzer is going to be identifying a sequence of tokens along with its pattern here nothing but the description for a token, whether it is an identifier, constant, reserved word, keyword, or an operator. If it is an operator, which type of the operator. So in the way it defines or it identifies the number of tokens present throughout the source program along with its patterns. So now the input to the parser is the token. By considering this token, every time it receives a token, a parser again asks for the to generate the next token. Like that, a sequence of tokens will be forwarded from the lexical analyzer and it will be received by the parser. So after receiving all the tokens, but with the help of these tokens, the parser is going to be constructing a parse tree, and the remaining these phases will be executed whenever this parse tree generated properly, and it will be given as the input towards the next phase. So now we are going to be discussing about the role of the parser here. So we are concentrating on the second phase, that is the parser. So if all tokens received are the meaningful, then it will be properly constructed a parse tree by following the hierarchical pattern from the root node towards the leaf nodes. If any error has been identified, then it will be reported to the error handler. So here it will be having the error handler. All this information will be stored in the symbol table. So if the parser tree has been generated properly, then this parse tree will be given as the input towards the next phase, that is the third phase, that is the semantic analyzer. So here the construction of the parser will be having some rules to be followed. We'll discuss about it. So here I have given a few points regarding the role of the parser. So it is a program that takes input string. Suppose if we consider an input string W, which is nothing but a set of or a sequence of tokens, and it is going to be produced as the output, either a parse tree or the error message. If the received tokens are having the proper meaning, then it can able to construct a parse tree. Otherwise, if it identifies any unrecognized token, then it will be reported as the error message towards the error handler. So the main goal of the parser here is to determine the semantic validation of a source string, whether a string is valid or not. If the tree is built, then the subsequent phases of the computer will be as usual considered, and the flow will completes by generating the low level language. So here the tree which is constructed by the semantic analyzer is reflecting the sequence of derivations or reductions, if any, needed during the parser. So we can call this process, that is the deriving or if it is possible, it can be reduction can also be done. Either these two processes can be done. We call it as the construction of a parts tree. So here the elementary subtree in the parts tree corresponds to a production of the grammar. So we'll see the parts tree here, the construction will follows the context free grammar. The grammar which is followed by the construction of a parts tree, we can say it is a context free grammar. We all know that the context free grammar is going to be following the 4 tuples that we can represent it as G is equal to V, T, P and S, whereas V stands for the finite set of variables or non-terminals. We can call it as the non-terminals. So these non-terminals are going to be producing some productions, and whereas T is nothing but a finite set of terminals where V and T do not intersect with each other. So here terminals are nothing but the small letters within the grammar, and P stands for, it is the productions. So each form of the production will be some non-terminal which produces a sequence of terminals or non-terminals. So here A is nothing but a non-terminal and alpha is a terminal. So a production is a combination of the terminals and the non-terminals, but at LHS side it should consist of a non-terminal. A non-terminal can produce any number of or any sequence of or any combination of terminals and non-terminals here. So and sometimes these alpha can be an epsilon also. Epsilon is nothing but here null value. Epsilon is nothing but here null value. And S indicates the starting non-terminal. Yes, a starting non-terminal. The within the grammar, which non-terminal is written first by producing some production, then that non-terminal will be considered as the start symbol in the grammar. So next we'll see how the derivation of a given grammar can be done. So here again in the derivations, it can do either a leftmost derivation and the rightmost derivation. So first of all we'll see what is derivation. A derivation is nothing but we are going to be substituting the production rules, or we can say we can rewrite the rules by generating some string. With the help of a grammar, by substituting its productions in its place, or by substituting a production in the place of some non-terminal, we can able to get some sequence of string, that we call it as a derivation. And in the derivation again it is going to be following the leftmost derivation and the rightmost derivation. So leftmost derivation is nothing but replacing of a non-terminal with its production will be done from left towards right, and vice versa. Rightmost derivation is going to be following substitution of a production in the place of the non-terminal, starting from right moving towards the left. So here we have one grammar here. Some let's take some E derives E plus E, and same E derives E into E, and E derives minus E, and E derives ID. So we have this grammar which I have given here. I have written in the sequence of productions here, and we should derive a string, nothing but a string equal to, we have here minus brackets ID plus ID. So by using this grammar, by rewriting the rules, that is nothing but in the place of a non-terminal we can substitute any of these productions in the place of E. By substituting it or by elaborating it, we should derive the string minus of ID plus ID. So this can be done by using either a leftmost derivation or the rightmost derivation. We can form any of these types. So here let's see, for this we can have, suppose for this first try to construct a parse tree. So here start state is E, so I'll take the root node as E, and we should get E derives E plus E is there, E to E is there, minus E is there, and ID is there. So that to get a string minus id plus id, we have to choose a proper substitution of this non-terminal. So the string starts with minus, so that I'm considering the production 3 here. So E is going to be deriving minus and E. So I have achieved the string, the first character, that is minus. So now in the place of this E, now I have to choose which production to be substituted. So in my string I have plus, no into is there. So I can substitute the production 1 in the place of E. So that I am considering E plus E. E plus E. Sorry, I have forgotten here to write one more production, that is E within brackets. So E within brackets. So before addition, I have the string within the brackets. So that first after minus, the string should start with the open bracket. So which grammar can be able to derive it? This is the production where I can use it. So open bracket, E and the close bracket and the close bracket. Close bracket. So now I got minus open bracket, and now I should get id plus id. So in the place of here E, I can able to substitute the first one, that is the E plus E. Now I got minus open bracket and plus. So only I should get is in the place of non-terminals, I should get the integers. It is the integers. So in the place of E, now I can substitute the id. So in the place of E, I'll substitute id, and in the place of this E, I'll substitute id. Now you can read the string from the left towards the right. What I have? Minus, this is completed. Afterwards open bracket, afterwards id, afterwards plus, afterwards id, and then closing bracket. So we can able to derive the string minus of id plus id by using this grammar. So now in this parts tree, you can able to observe we have used the elaboration by substituting a non-terminal by using its production rules. So this is actually the parts tree what just now I have explained. So first considered E and minus E, then E within brackets, and then E plus E, then E will be replaced with the IDs. So we can achieve the given string by using the given grammar. And see this, how the leftmost derivation and the rightmost derivation can be performed by the parts tree. So coming to the leftmost derivation, a derivation is leftmost if at each step in the derivation a production is applied to the leftmost non-terminal in the sentinel form. So here we have considered the same grammar similar to previous one we have taken here. Right, so example is E can derive E plus E, E minus E, E into E, E by E, and minus E, and E within brackets and ID. So for this same grammar, we are going to be seeing now the leftmost derivation and the rightmost derivation. Right, so same, we'll consider the same string. We have to achieve the string. Some string is equal to minus of ID plus ID. You can consider the same one, same string. So now first E derives as usual, minus is there, so that we have considered minus E. After minus we have to get open brackets, so E derives minus same as it is will be there. In the place of E, in the place of this E, we have derived the open bracket E and E. So as of now we have only the one non-terminal at the RHS side, so that we have derived only that production. As it is a leftmost derivation, as the definition defines that the production should be applied at the leftmost non-terminal available in the sentinel form. So now coming to the step 3, here we have the two non-terminals E plus E. So as we are following the leftmost derivation, first we have to substitute left side non-terminal with this production, and right side non-terminal we are going to be writing as it is. At the next step, now we are going to be replacing the right non-terminal with its production, which gives a difference between the leftmost derivation and the rightmost derivation. So you can observe quite opposite between the leftmost derivation and the rightmost derivation. So the rightmost derivation defines that the production is applied at the RHS side non-terminal in the sentinel form. So in the step 3, in the leftmost derivation, we started the applied the production by using the leftmost E, but here in the rightmost derivation, we have to substitute first which is available at the RHS side, that is the right side. So now this E is replaced with ID, which is available at the right side, and now the left side E will be replaced. So finally, by using leftmost derivation or a rightmost derivation, by using both type of derivations, we can able to derive the necessary string, that is minus of ID plus ID. So such type of situations, we can call this grammar is a ambiguous grammar, or we can call it as the ambiguity. Ambiguity is nothing but, ambiguity defines that more than one parse tree in the different way can be constructed with the same grammar to derive the same string. So nothing but by using the same grammar to get a desired output string, we can able to perform parse tree, or we can able to construct a parse tree by more than one type. Either we can use more than one type of leftmost derivation or more than one type of rightmost derivation. Such cases we can call the grammar is the ambiguous. But here construction of a parse tree can be done in two different approaches, that is the top-down approach and the bottom-up approach. Top-down approach is nothing but starts with the root node and reaches towards the leaf nodes, and that is nothing but the end of the parse tree. And the bottom-up approach is nothing but starts with the leaf nodes and reaches towards the root nodes, starting from the lowest towards the highest. Either of these two approaches can be used to construct a parse tree. So to either of these two approaches, the grammar should not be in the form of ambiguous. So before applying any top-down or bottom-up approaches for construction of a parse tree, or to accept whether a string is accepted by the given grammar or not, the grammar should be unambiguous. The grammar should be unambiguous. Nothing but for a given grammar, it should be possible only the construction of one parse tree. Not more than one parse tree can be constructed by using a grammar. Then we can say that grammar is a unambiguous grammar. So this is about the role of a parser. That is nothing but how a parse tree can be constructed in the second phase of the compiler design. That is the in different phases of the compiler design. The second phase role is how the parser will consider the tokens and how it is going to be constructing a parse tree, and how the grammar can be derived. Either it can follow the leftmost derivation and the rightmost derivation. Thank you.